This section on Class B multi-engine performance will deal with the JA regulations for all phases of flight for that class of aeroplane. The regulations are all found in JAROPS 1, which we discussed briefly in the lesson on performance standards. However, most of these regulations can also be found in CAP 698. In this first lesson, we will discuss the regulations which are associated with the takeoff phase of flight. However, first of all, there are some general considerations we need to discuss before the takeoff regulations are examined. Paragraph 1.1 of CAP 698 on page 1 of section 3 simply describes the specimen aeroplane used in the CAP 698 manual. The specimen aeroplane for Class B multi-engine performance is a Piper Seneca 2. CAP 698 confirms that this aeroplane is classified as Performance Class B, and goes on to remind you in paragraph 1.2 of the definition of a Class B aeroplane. Class B aeroplanes are all propeller-driven aeroplanes having 9 or less passenger seats and a maximum takeoff mass of 5,700 kilograms or less. CAP 698 also states that performance accountability with one engine inoperative need not be considered below 300 feet. Further down on page 1 of section 3 are the regulations specific to the takeoff phase of flight. There are 2 principal regulations that must be complied with for takeoff. The first relates to the minimum field lengths that must be available for takeoff, and the second relates to the climb gradient after takeoff. This latter requirement will be dealt with in the next lesson. These takeoff requirements are exactly the same as those for the single-engine Class B aeroplane. The takeoff requirements state that if no clearway or stopway is available at the airfield, the takeoff distance, multiplied by 1.25, must not exceed the length of takeoff run available. This is best understood looking at an example. Let us assume that the aeroplane flight manual gives the takeoff distance as 4,000 feet. Multiplying this value by 1.25 gives us a value of 5,000 feet. Essentially, this means that the runway must be at least 5,000 feet long, or, more correctly, the takeoff run available must be at least 5,000 feet long. This rule ensures that once the aeroplane has completed the takeoff, that is, when the aeroplane has reached the screen height, there should be a certain amount of the runway still remaining. Therefore, the regulation requirement provides a safety margin for the takeoff. We discussed these safety concerns during the lesson on performance standards. The strict interpretation of this particular regulation is that although the actual takeoff distance is 4,000 feet, the authorities are suggesting that the worst case in a million would be a takeoff that is 5,000 feet. This fact helps us to see the difference between net and gross performance. Here, the gross performance for takeoff is 4,000 feet, but the net performance, which is always worse than the gross performance, is 5,000 feet. If there are stopways and/or clearways, then the requirements are a little more complicated. At airfields with stopways and/or clearways, there are 3 regulatory concerns about the takeoff distance. Firstly, when a stopway and/or clearway is available, the takeoff distance must not exceed the takeoff run available. Secondly, the takeoff distance, when multiplied by 1.3, must not exceed the accelerate stop distance available. Thirdly, the takeoff distance, when multiplied by 1.15, must not exceed the takeoff distance available. Since these regulations may be a little complicated to understand, let's work through an example to illustrate their meaning. We will assume a takeoff distance of 4,000 feet. The first regulation tells us that the takeoff distance of 4,000 feet must not exceed the takeoff run available. Therefore, the pilot must ensure that the runway, or more correctly the takeoff run available, is at least 4,000 feet long. The second regulation tells us that when the takeoff distance is multiplied by 1.3, that distance must not exceed the accelerate stop distance available. You may recall that the accelerate stop distance available is the takeoff run available plus any stopway. So, a pilot must ensure that the airfield has an accelerate stop distance available of more than 5,200 feet long. The last regulation tells us that the takeoff distance, when multiplied by 1.15, must not exceed the takeoff distance available. You may recall that the takeoff distance available is the takeoff run available plus any clearway. Therefore, the pilot must ensure that he has at least 4,600 feet of takeoff distance available. If any of these regulations cannot be complied with, the pilot must reduce his takeoff distance. The most practical method of doing this is to take off with less weight. Perhaps use a higher flap setting, or wait till the air density is increased to increase the aircraft's performance. Having discussed the regulations detailing the maximum takeoff distance that may be permitted at an airfield, this next part of the lesson will detail the regulations governing how the takeoff distance is corrected for non-standard conditions. These regulations stipulate what correction factors must be applied to the takeoff distance when the runway conditions are different from standard. At the top of page 1, section 3, under paragraph C, in the CAP 698, it states that if the runway is other than dry and paved, the following correction factors must be used when determining the takeoff distance. These correction factors are shown on screen. As you have learned already, grass runways will increase the takeoff distance compared to paved runways. Here, the factor to account for the effect of dry grass on the takeoff distance is 1.2, and 1.3 if the grass is wet. On the next page, point D details the corrections to be applied if there is a slope to the runway. Point D states that a pilot must increase the takeoff distance by 5% or by a factor of 1.05 for every 1% upslope. However, it also states that no factorization is permitted for downslope. In other words, if an aeroplane is to take off on a downward sloping runway, no correction factor is to be applied for the downslope. The reason for ignoring the downslope is because a downslope will decrease the takeoff distance. This adds a little extra safety margin to the takeoff distance calculation.